Hello folks, I'm Mike, coming back at you with another video on precalculus. In the previous video, we talked about polynomial and rational inequalities and how we solve those guys. In this video, we're going to take a look at modeling using variation. Now, there are different ways that two unknown quantities, yet related at the same time, typically x and y, could be t and y, or whatever, but there are some different ways that two quantities can vary with each other. There are three different types of variation that we're going to talk about in this video. There's direct variation, there's inverse variation, and then sometimes you have three or more quantities that relate to each other somehow, and those are in joint variation. So let's just get right into what each of these three types of variations are saying. For direct variation, we say that y varies directly with x, or y is directly proportional to x if y is equal to k times x, where k is the constant of variation. You can see that this looks like a linear equation, a line type thing is happening here. This is what we mean by it varies directly. As x changes by something, y changes in the same way. So this is the general model that we use to show direct variation. Indirect variation, or inverse variation, we say that y varies inversely with x, or we say that y is inversely proportional to x if y is equal to k over x, where k is the constant of variation. Note here that when x does one thing, y does the opposite. If x gets smaller, then y gets larger. If x gets larger, y gets smaller. For direct variation, what one does, the other one does as well. If x decreases, so does y. If x increases, so does y. And then we had that third case where we could have three or more things varying with each other. So this is an example of joint variation. We say that y varies jointly with w and x, or we say that y is jointly proportional to w and x if y is equal to k times w times x, where k is, again, that constant of variation. Similar to direct variation, but here we have two unknowns, or two things that multiply with each other and this constant of variation, and we get y. That constant of variation, k, in every type of problem that we see in this video and in the section, that is sort of an unknown constant that we are going to be solving for. So when we solve these variation problems, on that note, we use the same general process regardless of the particular type of variation that we have. To solve variation problems, one, write the appropriate variation model as described in the given problem with the variables in the given problem. This is the first hurdle that people will get tripped up on. That hurdle being using the wrong variation model based on what the problem says. If the problem says varies directly with blank, then that's a direct variation model. If it says varies inversely with, then use that model. Or if it says varies jointly with blank and blank, then there's another multiplication type of thing happening in there. Next, you're going to substitute in a known value for the variables, which will be given to you in the statement of the problem, and you're going to use that known value to solve for k. Then you're going to substitute that k value back into the model that you created in step 1, and this is the final model that you're going to use to answer all parts of the problem. But first, let's just get some practice with writing some models first based on the description that you are given. First one here, y varies inversely with the square of t. So when you read these kinds of things, you see y varies inversely with, and then in this case, the square of t afterwards. Look at the keywords varies inversely with, varies blank with. That tells you what type of model you are going to be using here. In this case, we are going to use an inverse variation model, so it's going to be something over something is equal to something else. That thing that's equal to something else comes before this. So y varies inversely with blank. So this is saying y will equal something over something. This is an inverse variation model. So on the top, we always have that constant of variation k. And then afterwards, after the varies inversely with, we see that it says the square of t. So that's telling us that that thing that's going to be on the bottom is going to be the square of t, or t squared. So this is a general model that we would be working with if we saw a problem that had this kind of variation happening. This is how we would write y varies inversely with the square of t. Next up, p varies directly with 5 times z. So again, you're looking for those keywords varies blank with, and whatever's in that blank, that tells you what kind of variation model you're going to use. Here we're using a direct variation model. What goes on the left-hand side of the equal sign is what comes before our 3-word phrase here. So it's going to be p equals, we have that constant of variation k, and then we have our other quantity. This says 5 times z. So p is equal to k times 5z, which is the same thing as 5 times k times z. So this is the model that we would be working with here. S varies jointly with the square root of w and the cube of x. This one certainly a little bit more complicated, but we're still going to do the same kind of thing. We see varies jointly with, so this is a joint variation model that we're going to be using. Something is equal to k times something else times another something else. What goes on the left-hand side of that equal sign? The s here. So s equals, we have k, the constant of variation, times the first next something, the square root of w, and the cube of x. What follows the and is the second thing that goes, that second something else that goes on the right-hand side, the cube of x, aka x cubed. So our model is s equals k times the square root of w times x cubed, or k times x cubed times the square root of w. So hopefully these made sense. These are just a few practice problems where we get used to writing models. So let's actually see some practice problems here. Let's see how we would solve these variation problems. The amount of medication a doctor prescribes for a child varies directly with the weight of the child. Studies have shown that 11 milligrams of this medication should be given to a 40-pound child. How much should be given to a 70-pound child? Another question here, how much should a child weigh in order to receive a 13.5 milligram dose? So we are reading the question first to get just what type of variation model are we going to be working with here. We have the amount of medication varies directly with our weight. So we can give these things whatever letter name we want to. I called M the amount of medication or the amount of medicine, and I let W be the weight of the child. The question said that these things vary directly, so M is going to equal K times W. So this was step one in our four-step process. We just set up the model that we're using here. Next step, we're going to take a known value. We're going to take a known point, if you will, plug it into this model here, and we're going to solve for our constant of variation K. Now, what's the point that we know? We know that if the weight of the child is 40 pounds, then the amount of medicine they get is 11 milligrams. So making that substitution, I know that 11 is equal to K times 40, or 40K. I can divide both sides by 40, and that tells me that K is 0.275. So I'm going to take this value of K, I'm going to substitute it back into the model I got from step one, and this is the final model that we are going to be using. This is what we're going to use to actually solve the given problem. So M is equal to 0.275 times W. So now let's answer the two questions that we had to answer. To find the amount of medicine needed for a 70-pound child, you're simply going to substitute in 70 for W, and you do the multiplication, you get 19.25 milligrams. To find the weight needed for a 13.5 milligram dose, this is our M value, so we're substituting in 13.5 for M, and then we are going to solve for the letter W. So 13.5 equals 0.275 W, dividing both sides by 0.275. I would say round to, say, the nearest whole number or the nearest tenth or whatever. 13.5 divided by 0.275 is 49.090909 which is approximately 49 pounds. So there we go. This is our first sample here where we solve a variation problem using a variation model. We'll do one more here. Kinetic energy varies jointly with the mass of an object and the square of the velocity of the object. An object with a mass of 5 kilograms and moves with a velocity of 7 meters per second has kinetic energy of 122.5 joules. What is the mass of an object traveling at a velocity of 12 meters per second and has a kinetic energy of 800 joules? So, fairly long problem, whole lot of information happening in there, but still, let's go through our four-step process. First thing, we just need to identify the kind of model that we are going to use here. If we read our first sentence, it says kinetic energy varies jointly with the mass of an object and the square of the velocity of the object. So what's underlined in gray there tells us what type of model we need to use. We need to use a joint variation model. Kinetic energy, you can give it whatever name you want, varies jointly with, aka will equal, our constant of variation k times the mass of the object times the velocity squared. That's the square of the velocity. So here's what I chose to use as the names for each of these quantities. I used Ke for kinetic energy equals K times m for the mass times v squared, v standing for the velocity of the object. Again, this was step one. We're just setting up our variation model. Step two, we're going to take known values for kinetic energy, mass, and velocity, and we're going to substitute them in and solve for our k value. So we know that when the mass is 5 and the velocity is 7, the kinetic energy is 122.5. So we're going to make these substitutions. 5 goes in for m, 7 goes in for v, and 122.5 goes in for ke. Well, 122.5 gives me k times 5 times 7 squared. 7 squared is 49. 49 times 5 is 245. So we have 122.5 is equal to 245k. I solve for k by dividing both sides by 245, and thus k is equal to a positive 1/2. So now we have our model. Kinetic energy equals 1/2 times the mass times the velocity squared. And just as a side note, before we continue on with solving this question, if you don't recall high school physics or you didn't take physics, this is the actual formula for kinetic energy of an object in motion. It is truly indeed Ke equals 1/2 mv squared. So the question said, what's the mass of an object traveling at a velocity of 12 meters per second and has a kinetic energy of 800 joules? So we are going to make those substitutions. 800 goes in for Ke, 12 goes in for V, and we're going to solve for M. So 800 is 1/2 times the mass times 12 squared. 12 squared is 144. So 144 times 1/2 is 72. That's where we get our 72m. To solve for m, divide both sides by 72, and we get 872, or 100 over 9, or 11.111 repeating kilograms. And again, I would typically say round your answer to the nearest whole number or nearest tenth or something like that. But these were a couple sample problems involving variation models. Key thing really is to be sure you read the word problem carefully. You're using the appropriate model from the information that's given to you in that word problem, and then substituting in a known value to find your K, substituting back in for K, and then solving your given problem. Guys, if you have any questions, please be sure to reach out to me. Send me emails, send me texts, show up at my front door, flare signals going up into the sky, SOSs on the beach. Anything you have to do. Otherwise, until the next video, take it easy, guys.